The floor is yours. So the idea was also to, let's say, bring some demonstration and give the opportunity for people to present the toolbox that are really in the scope of this workshop. So Mathieu, the floor is yours. You have 45 minutes. Will be a little bit over the time for Europeans. That's a bit late, but still you have 45 minutes, and it's my great pleasure to give you the floor for this demonstration. Thank you very much.
Yeah, thank you, Jant, and yeah, of course, thank you very much for having us. Can you see my screen?
Yes, we can, but I don't know if you want to put that in full screen.
Yes, then I will go on full screen now.
Yeah.
And
perfect.
Okay. And yeah, what Beat and I, what we thought we would like to do in these 45 minutes is, yeah, to give a demonstration and walk through the Adversarial Robustness Toolbox. So I just show a few slides, so telling you a bit about the background, the scope of the big picture. But then, yeah, we would like to show you an actual demo and walk a bit more in detail through how you can do different kinds of adversarial machine learning evaluations with ART. We could then dive deeper into a few aspects, perhaps also depending on everybody's interest. And then I was planning to conclude with an outlook on our roadmap for this project, share some of the resources, and also share some information how to contribute to this open source project for those of you who are interested in that. If you have any questions, and of course we can leave some discussion to the end, but yeah, please interrupt me at any point if you have any questions or comments. I don't think in this presentation mode I can see the list of participants, so I wouldn't see if you raise hands there. So please just speak up and interrupt me if you have any questions.
So in fact, normally you should be able to see if somebody raises hands on the top
okay.
of your Microsoft Teams. You have some highlight, let's say, on the participants. I raised my hand just for the test. Yeah, I don't know if you see it.
I don't see it in this full
screen. All right. Well, yeah, because you're in full screen. Okay.
Mm-hmm. Okay. So yeah, what is ART? So the Adversarial Robustness Toolbox is a Python library for machine learning security. It's an open source project that we started at IBM around 3 years ago. So it's fully open source, available on GitHub. Since we released it back then, yeah, it has received a good amount of users, followers, so a good amount of GitHub stars, forks, etc. The purpose of ART is to support the evaluation of machine learning models against different adversarial threats, and also applying common baseline defenses. With ART, I believe we are probably the most comprehensive adversarial machine learning library out there. And that's in terms of the threats that we address. I believe a lot of the discussions here in the workshop have been around evasion attacks. But in ART, we also look more broadly or beyond that and support poisoning attacks, also extraction or inference attacks. I will talk about that in a moment a little more. We are also quite broad in the type of machine learning tasks that we support. So initially we started with image classification, which is probably still kind of the most widely considered use case or domain in the literature. But over time, we have expanded that to other types of machine learning tasks like object detection, We added automated speech recognition last year, and planning to add even more tasks going forward. ART is also broad in terms of the machine learning frameworks that it supports. So we started with support for the most popular deep learning frameworks, TensorFlow, Keras, PyTorch, but then over time also added capabilities for more conventional machine learning types of models and frameworks like scikit-learn, XGBoost, etc. And then finally, in terms of the data that ART can be applied to, as I said, we started with images, as this is what a lot of the literatures had been focusing on. But then over time, we added also support for tabular data, audio, video data, and most recently also for multimodal input data sources. Just to say a little bit more about the different threats that I mentioned. So evasion attacks, I believe this has been probably what many of the discussions in this workshop have been centered around, where of course the adversary tries to modify the input to a machine learning model in order to influence its output in a particular way. But of course, there exist other types of threats that are important to consider, like poisoning attacks, where the attacker tampers with the training data that the machine learning model is trained on, and thereby, for instance, insert backdoors, which then later on can be exploited to mount evasion attacks more efficiently. In an extraction attack, the attacker tries to steal a proprietary machine learning model through querying the model in a smart way, and thus creating a local replica of the proprietary model. And finally, in an inference attack, the attacker would try to, again, through typically querying the model, infer sensitive information, private information that was contained in the training data, as such information can leak into. And what is interesting, and people have actually observed this in practice, is that when you think about these combinations, some of the attacks can actually become much stronger. So for instance, there's a number of examples where attackers first mounted an extraction attack to learn about the target model, query a local replica of the model, and then ultimately mount their evasion attack in a white box setting. And similarly, you could imagine that the same applies if the attacker wanted to do an inference attack and infer private or sensitive properties from the training data set. And then, this is what I usually show when I talk about this. I don't think I need to convince most of the people here in the workshop that, I mean, these are real threats with quite a few actual vulnerabilities having been reported. Many of them in the cybersecurity domain. So when you apply machine learning models, for instance, to detect malware, but in other domains and in other applications too, of course. So what we then provide with ART is the tools to examine and to evaluate machine learning models under these different types of threats. So in that sense, for each of these four threats, evasion, poisoning, extraction, and inference, we provide with ART both state-of-the-art attacks, so that one can empirically assess how vulnerable a given model is with regard to these attacks. And then on the other hand, we also provide state-of-the-art baseline defenses than what one could explore to assess how effective such baseline defenses would be, and also in order to benchmark novel defenses against these type of baselines. So you can see, so the numbers in the table indicate the absolute number of attacks and defenses that we have for each of these 4 attack threads. And then in brackets, that's kind of the number of attacks that we added in some of our more recent releases. Then I'd like to go through now a demonstration and walkthrough. So I hope you can still see the screen.
Yes, it works, yes.
Good. So yeah, this is the GitHub organization where the Adversarial Robustness Toolbox is hosted. I said a moment ago, so it started as an IBM research project, but actually mid of last year, it was incubated by the Linux Foundation for AI, actually along with 2 other IBM research projects for fairness of AI and explainability of AI. So that's where we host it now. And so I think when you go to the repo, I think a good place to explore, a good place to get started is the wiki that we have. So which, and I think this is what I just showed you, so kind of gives, I think, a good, good starting point and good references to get started exploring art, attacks, defenses, the type of models that we support. Maybe I just start there because that's kind of the most fundamental things. So originally, the type of models that can be evaluated, we called them classifiers, because initially we focused a lot on classification, but then last year we generalized that to estimators, kind of like in a scikit-learn philosophy to encompass a broader class of machine learning models. So you can see that still, we have particularly vast support or broad support for different classification models, as I said, in many of the popular deep learning frameworks, but also in conventional machine learning model frameworks. Then we added recently object, and so we have, for RCNN type of object detection, and also speech recognition and ASR models like deep speech or Lingvo-based automated speech recognition models readily available in art. On the attack side, then you can start exploring the type of evasion, poisoning, extraction, and inference attacks that we have. On the defense side, we have a number of adversarial training protocols supported in art. We have pre-processing and post-processing defenses available in art, and I will show in a moment in how those can be easily applied. We also have defensive approaches like transformation of models, for instance, through distillation or through certain types of techniques that can be used to clean poisoning from trained machine learning models. And then finally, we also have a number of detection methods on the defensive side available in art. Maybe, let me then show you perhaps how to best get started. So you can easily pip install art. If you then clone the repository, you will have available and have access to a broad number of examples that show you how to do different things with art. But what's perhaps the kind of most intuitive way to get started is the notebooks that we have in art, which demonstrate the usage of art across pretty much all the threads, pretty much all the machine learning tasks, and also data modalities that art supports. So here, just as an illustration at the top, you see an example of a adversarial sample created by art against the action recognition system with a corresponding notebook that shows how to generate that. Now, the one notebook that I'd like to spend a bit more time on and walk you through is a notebook that illustrates on an image classification task how to use art end to end. So and this is one of the notebooks that come with the repo. So there, what I will quickly walk you through is how you can work with the Keras image classifier in art and how to wrap it into an art object. How you then can, with very few lines of code, mount state-of-the-art attacks against that classifier. How you can also deploy defenses against such attacks. And then finally, and that's of course, where really the research methodology is at this point, where you can also easily create adaptive attacks that can bypass those defenses. So quickly walking through this. So what you do after kind of making all the imports, which is really just Keras in this case. So we're going to use a Keras Resonance 50 model and then the corresponding art objects and art classes to work with that model. We're going to download a small stub of ImageNet images, which we're going to load here. So in total, you could, so those are 224 times 224 images, colored images. For, I think the default in this notebook is we kind of pin to this image. Then, what you would normally do when you work with, say, plain Keras, so you load the ResNet model that ships with Keras. After you loaded that, you'll be then able to call it and not surprisingly or correctly, the ResNet 50 models outputs correctly the ImageNet class monocycle or unicycle. Now, in order to use art and apply some of the adversarial techniques, all you need to do is really write this amount of code, like in these two cells, 7 and 8. So the first part is what actually Keras expects you to do before you apply the ResNet 50 model is to do some pre-processing of the input, which basically it flips the color channels and it subtracts channel-wise means. So this is something that we can represent in an art preprocessor object. And after we've done that, we then create an art Keras classifier object, which as input takes the core kind of Keras ResNet 50 model. It takes the preprocessor class or object that we just created. And one thing we also need to tell art about is what's kind of the valid range of inputs, so that particularly when we generate adversarial examples, that those then lie within the permissible range. Now, the first thing we can then validate is that when we now call the predict function of the art classifier, which it exposes, we obtain the consistent result and the same result as what we would have obtained by working directly in Keras. Now, what we do have now with this art classifier object is an abstraction. which besides the predict function that we called here, also exposes other functions that are commonly used in adversarial machine learning. And perhaps the single most important function is the loss gradient. So where one thing we can do now with the art classifier is compute, and here we will also visualize the gradient of the loss with respect to the model input, which kind of gives you a saliency map, and which kind of tells you which parts of the input image is the classifier's loss most sensitive to. And not too surprisingly, you see most of the signals in a part of the original image where the actual unicycle lies. What we then can do next is do adversarial attacks. And now we can see how this ResNet 50 model performs under different adversarial attacks. So here we create an art instance of the art projected gradient descent class. We pass to it the art classifier that we just instantiated a moment ago. In this case here, we run an untargeted attack, and these are the parameters of the projected gradient descent attack that probably many of you know. So here the default is that we mount an attack with L infinity norm constraints, where epsilon, so 5, so that's the maximum perturbation in L infinity norm that this attack will allow for, and then these are just two hyperparameters. So and what we've done here then is to call this attack on the original input, on the benign input, and create an adversarial example, which we plot here, and for which we also show the output here, or the model's prediction here. So in this case, the prediction has changed. Originally it was a unicycle, now it's a mountain bike, what the model predicts, which is not too far off. But then on the other hand, it's an untargeted attack. So all we did require, or all that we aimed for with this attack, was to change the original classification, even though the classification was not too far. But of course, equally easy to do really is to mount a targeted attack, where what we are doing now is, and you could pick any of the 1,000 target classes from ImageNet. Here we're going to pick the target label 100, which is encodes the black swan, or represents black swan. What we do here is we now change the attack configuration to a targeted attack. Now, this time when we generate the adversarial example, again, we give it, we provide the attack, the original input, but here then also we provide it with a target label that we wish the classification of the adversarial example to result in. And so if we do that, then that will just take a few seconds. And then, really not surprisingly, the targeted attack is successful. Whereas the image, and this is the adversarial example that we're plotting here, to a human looks identical to the original input. And in order to quantify that, so we can also compute statistics and norms over the perturbation. And what we can see is, so the L infinity norm that we really controlled with this PGD attack is just below 2%, relatively, and also in the other norms, the perturbation is actually fairly low. So what I would show next is how to with art apply defenses, and then after that actually mount an adaptive attack against such defenses. But perhaps I'll just pause here for one moment to see if there's any questions thus far.
For me, it's perfectly clear and very straightforward in terms of using the library. I had one question that I wanted to ask before you started, but the notebook is just how many people are involved in this project, because it's quite impressive in the the amount of techniques that you have. Is it something that do you know how many people are involved in this project?
Yes, we have a large number of contributors now. So we, I think here it lists 51, I think was the number I saw a moment ago. And yeah, so we started as an IBM, started as a project within IBM. And yeah, over the first year or so, it was pretty much just our team who did the maintenance and development. This has grown now. So one activity that we're involved in since the beginning of last year is a research program launched by DARPA. So they're the DARPA GUARD program. So GUARD stands for Guaranteeing AI Robustness Against Deception. So that's a very large research program that they started beginning of last year to advance research on adversarial machine learning. And in that program, they're using art for the evaluation of novel defenses that are being developed under this program. So that's actually why has been the driving force to extend art to object detection, for instance, or to automated speech recognition, because those are the type of scenarios that then DARPA and I suppose at the end of the day the Department of Defense are particularly interested in. And through that project, we received then also more contributions from other partners and participants in that program. So I think we have now actually in our authors file also officially listed a few other external organization that started to work with us, both from academia but also from industry. And we expect that list to further grow.
Okay, thank you.
In the future. All right, then, going to having a look at the defenses. Course, it's not difficult to come up with ideas how one could try to defend against these types of adversarial perturbations. And I think a couple of years ago, kind of when really the research in this area took off, there were a number of papers which proposed such defenses along the lines of this one here, which is spatial smoothing, where the idea is to do some sort of signal processing on the inputs to a machine learning model and try to filter out the kind of adversarial perturbation and render the adversarial examples ineffective. And so in art, we support some of these types of signal pre-processing defenses. Spatial smoothing is one of them, which is parameterized by the window size. And so what then this defense does is it just applies a low pass filter over the image within a window of size 3. It just takes the average pixel average and returns a smooth version of the original input. And of course, so if we do that, I think we want two things. So one thing is when we apply that to the original input, so non-adversarial to a benign input, we still want the model to give accurate predictions. So we don't want to filter away too much useful information. But then on the other hand, when we apply the spatial smoothing defense to an adversarial input, we would like then this the smoothed input to be correctly classified again. And what we can see here when we run this cell is that this very simple defense at first sight seems to be effective in both these regards. So on the original sample, when we apply spatial smoothing, the model is still able to correctly predict that this image shows a unicycle. And on the adversarial example that we just produced a moment ago, if we apply the spatial smoothing defense to that one, then indeed the model is not fooled anymore, and kind of the smoothing got rid of the adversarial signal. Now this, and of course this has then, and then mostly with the work of Atelier and Nicolas Carlini, be shown to actually be somewhat misleading, or actually giving what one should consider a false sense of security, because if the attacker is aware that such a defense is put in place, it is actually pretty straightforward for the attacker to produce adversarial examples that kind of survive these type of pre-processing defenses, and that are will go through these kind of pre-processing defenses. And this is also not, this is then one thing that also ART allows one to do. And so in order to do that, what we do here is we create a new classifier object, so which is again a Keras classifier, where we now apply or kind of make the spatial smoothing pre-processing defense a part of the classifier. And what that first results in, so I mean the first thing we can check is if we apply this kind of defended classifier and use this defended classifier to predict the adversarial example that we produced above, it gives us kind of what we just saw a moment ago. So it shows us what how the at first sight this classifier seems to be able to defend against adversarial examples. But the issue now is that if we now mount an attack against the defended classifier, adversarial examples that survive the spatial. And so the way we can mount this is that now we create a projected gradient descent instance in ART. This time we pass it the defended classifier. The remaining configuration is largely the same, so still we want to mount a targeted attack. And now what happens? So if we apply now and run this attack against the defended classifier, we'll still be able to create an adversarial example, albeit the classifier tries to defend against this adversarial example with a spatial smoothing defense. So we can see in the end this adaptive white box attack turns out to be successful. And and again, same as before, we can also compute some metrics over that adversarial example, but it hasn't increased. So the perturbation norms even haven't increased that much. So this is the one demonstration that I wanted to walk through end to end. I'll just maybe point out that there are many more notebooks that you could look at to explore different capabilities of ART. So as I said a bit earlier, so for instance, you can look at how to use ART on different types of data, like video data or audio data. You can look how to do adversarial training with ART. We also have support in ART, and that's what this image here now in the center shows, to create adversarial patches. And so yeah, attacks that then go more towards adversarial examples that you could also realize in the physical domain. We have demonstrations of how to work, how to mount attacks against black box models, so gradient-free attacks. And so one, I think, nice illustration that we have is how to fool a Tesseract OCR system. And yeah, there's much more. Of course, there's also then, like, yeah, on some of the other attack vectors, the other threats that I mentioned earlier. So I think we have some nice notebooks also demonstrating the poisoning capabilities in art. So there's a lot to explore there. I'll leave that there then and just go back to the slide deck. And yeah, I think I will start to conclude. So I had a bit more information about the different threats and some of the capabilities that we have in art, but I think we saw some of that now already. Just in terms of the roadmap for art, so yeah, we are now on a kind of quarterly release schedule, which some of which is driven by the DARPA GUARD program that I mentioned, which we're participating in. So we just had actually in December our 1.5 release, where we added more capabilities for automated speech recognition evaluations, etc. I think going forward, and not sure if we will have all of that for the next release in March 1.6, but definitely this year we will work towards having broader support for physical world threat models, supporting models with discrete inputs. One special case of that, models that work on text inputs. I think discrete inputs are also particularly interesting or important in applications of machine learning in the cybersecurity domain. And yeah, definitely we are thinking beyond that. I think down the road, we would love to also support other types of machine learning tasks like regression models, potentially also take it to reinforcement learning models and the respective adversarial attacks and defenses for those. And for sure, constantly improving performance of art and usability of art based on user feedback is something that we continuously do. Some to share. So we saw the GitHub repository, and there's the extensive documentation available. We have a Slack channel that we use for interactions with our users. And perhaps the last thing at the bottom of this page that I'd like to call out, since we moved and art moved under the Linux Foundation AI last year, we've had really good interactions with users in our monthly Trusted AI committee meetings. So there were, for instance, users from Microsoft or from General Motors who talked about how they are using art and what use cases they are using art for, and sharing some of the insights and lessons that they learned. In case you're interested in contributing, I suggest check out the contributions page that we have in our GitHub repo, which provides, I think, a good entry point. Generally, if you're using art and you find anything that you suspect to be a bug, or if you see any room for improvements, any features that you think would be valuable to be added, we strongly encourage you to engage with us either via GitHub, just creating GitHub issues, or contact us on the Slack channel. Of course, we are always happy about contributions of bug fixes or perhaps even new features. And that's a fairly streamlined process to pull request those and have those contributions reviewed and contributed to art. And I think that's all I have. So thank you for the opportunity to present art to you, and I'll be happy to take any questions.
So Matthew, if I may, I also want to add that I know Jiayang is interested in clever scores, which the model agnostic robustness score we developed. I just want to mention this is also supported by art, so you can call the art function and then run this robustness score on any model you have.
Okay, nice. So thank you very much. It was really a great demonstration, and it's quite impressive to see also the rhythm of integration of new algorithms and also new usage that you do in art. It's many thanks for presenting that clearly and comprehensively. Thank you very much. But maybe there are other questions in the audience. I have to admit your presentation was really super clear and the demonstration was at the right pace and it's well packaged, so the interface is quite natural, I would say, to proceed for the attack, the defense and stuff like that. So thank you very much.
Thank you, Jane.
I do have a question.
Go on.
All right. So at Airbus, we're also working towards creating some algorithm that we may put open source at some point, because we clearly lacking a lot of manpower and we would like the community to contribute a bit to those working packages. So of course, we are nowhere near what Art is mentioning and the number of people that have been working on the toolbox, but I was naively wondering how many people do contribute on a monthly basis to provide you with codes or to contact you with bugs. How many are actually people that are just not really up to date to the level, just trying to contribute, but are not really, I would say, and not crackpot, but kind of people just throwing you some code that is useful and unuseful, just for us as we are entering in this realm of putting more open source algorithm into the open. Do you have any feedback on that?
So your question is how large the team is, or how?
Well, it's mostly, is the community really contributing to arts? Did you find new collaboration that really was sparkle with putting the code online? How many contact you was actually code that have no value for you, and how many contact you was actual constructive piece of algorithm?
Mm-hmm. I mean, I think the majority of the code base was still produced by our team. I think last year, I mean, we started to get really substantial contributions externally. So I mean, one example was I think work that from a university, Kyushu University, that had been published, and they wanted to contribute their attacks to art. And so we worked with them to on their pull request to make sure that it integrated. I think through the DARPA Guard program, we've been also getting some substantial contributions. And there, I think it's actually both kind of on the algorithmic side. So partners contributing algorithms that they developed and that they, I mean, in some cases already published, and would like more people to use those algorithms, and therefore thought, okay, maybe art is a good platform to integrate them with. But also more on the kind of like engineering side, we got very valuable contributions that helped us with performance gains. For instance, I mean, some of the pre-processing techniques that I mentioned, when you do those on, for instance, video data, it can become a bottleneck. So therefore, we got some very good kind of like deep learning engineering type of contributions as well.
In that case, had you listed your shortcomings, or they spontaneously propose a solution to your code?
This is more a continuous process. I mean, we have the GitHub issues where I mean, anyone can open an issue if they find something is not working or something is missing or something could be improved. And also ourselves. I mean, if we want to kind of put a placeholder out there for shortcomings that we know about and that perhaps we plan to address at some point, we also create such issues ourselves. And perhaps that is, I mean, even say beyond external partners contributing code and significant amount of code to the project, I think, of course, we have an extensive test suite for art, but still, I mean, people externally using art and kind of as soon as they observe something strange, posting and sharing that behavior just helps so much in terms of improving code quality and just finding bugs and improving the overall quality of the project continuously.
All right, thanks.
Yeah, that makes perfect sense. And okay, yeah. Do we have other questions from the audience? No. Well, I think we can close the session and the day, thanking again you, Mathieu, and all the people who collaborated to this demonstration. It was really very enlightening for me, at least, to discover that because I was maybe on an older version of art, and it has boomed since let's say 1 year or something like that, and it's great to see that, and you demonstrated that very well. Thank you very much.